Today we're going to talk about energy. Now, first of all, what is energy? Well, energy we define in physics as the ability to do work. Not a great definition, because what the heck does that mean? Well, work in physics means things that you accomplish. So it could mean lighting a light bulb, it could mean picking up an object and moving it somewhere else. That's work. So to do work, we need energy, and energy can come in all kinds of forms. Now, specifically in this picture, the energy that we're seeing is light energy, which is provided by electricity, which had to come from somewhere. So where do we get the energy that we're seeing in this picture right now? Well, it turns out that our cities are only so bright enough in fact you can see them from space, because we have multiple sources of energy that we can use to harness to create electricity, which is our primary means of transferring energy from one place to another efficiently. So what are these methods? Well, the primary method by which we move energy around or contain energy and use it is in the form of fossil fuels. What is a fossil fuel? Well, you've probably heard this before, but old species that were alive many, many millions of years ago, like dinosaurs and the plants and marine species that existed in their time, they died out. And then as their bodies were buried under the earth and were compacted by pressure and heat for many, many millions of years, those atoms in their body were pushed together and crushed into this form that you see now. We call these three different kinds of fossil fuels coal, oil, and gas. But really they all are the same thing. They're old, organic matter, primarily made out of carbon. So what are the things that we use fossil fuels for? Well, other than their primary function, which is to generate electricity from burning them, we have a lot of different end uses. We do put fossil fuels directly into our transportation vehicles, such as cars and planes and buses and trains, to get our own bodies and other things from place to place. But we also heat our homes with fossil fuels. We put it into the motors of our lawnmowers and things of that nature. We even cook sometimes with fossil fuels. And we store it in vast quantities, and we're taking it out of the earth at unprecedented rates, to the point where we're probably not going to have much more of this stuff after a couple hundred years. In fact, most activities that humans participate in can generally, nowadays, be traced back to some form of fossil fuel. Now, this wouldn't be a big deal if it wasn't for the fact that fossil fuels emit things called greenhouse gases, which I imagine you've heard of before. These are gases like carbon dioxide, methane, and many others that go into the atmosphere and trap heat. And it's causing something known as global warming, which I hope you've heard of before, and if not, Google it. So what can we do to prevent global warming and other things that can go wrong as a result of using too many fossil fuels? And by the way, we're not going to have them for much longer because they are typically referred to as a non-renewable resource for a reason. There are only so many dead dinosaurs in the ground left to dig up. So what are our alternatives? Well, there are many different kinds of alternative energy sources that we can use, and I'm going to try and list as many as I can today just so you can get an idea, a basic idea, I'm not going to go too in depth, of what our other choices are, because there are quite a few. So, alternative energy sources, and just as a couple examples, I'm going to go into more than just these four. We're seeing geothermal, hydroelectric, wind, and solar just on this one page. So, as we dive in, I'm first going to compare these alternative energy sources to the one that I was just discussing a moment ago, which is fossil fuels. And I'm just going to focus on coal, but the oil and natural gas processes is similar enough that we can pretty much understand fossil fuels to all work the same way. So, in this coal power plant, we have chemical energy that is stored inside of the coal that we dig out of the earth, and again, that's our dead dinosaurs and really primarily dead plants. That chemical energy converts into heat energy when we burn it, and the heat from the burning coal turns into the kinetic energy of steam. And as we know, kinetic energy just means the energy of motion, of things moving around and jittering. So the kinetic energy of the steam travels down a pipe where it turns a turbine, and that turbine turns a generator. Now, this is the complicated part. I'm not going to get too much into the science, but it's going to be important for you to know what a turbine and a generator is, and to kind of put them together, a little basic electromagnetism for you. If you have a magnet, one part north and one part south, and you put a wire inside of it and you spin the wire, you force it to move or to turn, then what's going to happen is electrons will be forced to flow through that wire. Now, if you've studied physics at all, you know that electricity is the flow of electrons. So if you can create moving electrons by spinning a wire through a magnet, then by doing the spinning, you've created electricity. So most of these technologies are going to rely on spinning a turbine, and that's going to create electricity in the generator. So that's just kind of a basic idea. So anyways, we have the turbine that's being turned by steam spinning it. Then the turbine cranks a generator, which creates electricity, and the electricity goes out to the public. Now there's a note here at the very top that 60% of the energy that we have in that coal actually is going to turn into waste energy in the form of heat. So there's going to be a lot of heat and other things coming out of this plant, and we can't usefully use that heat energy. What we can use is the 40% that gets converted into electricity energy, which we can use and send out for people to plug their iPhones into the wall and charge it. So that's what we get to keep, is the 40%. And that's because this process is about 40% efficient. So the term efficiency is coming in here. Hopefully you've studied that at this point. Now, a couple pros and cons about this whole system with coal or potentially oil and gas. Again, they're fairly similar to each other, all being fossil fuels. Pro would be that fossil fuels have a very high energy content. So for the amount of stuff packed into a hunk of coal or a sample of oil or a volume of natural gas, there is a lot of energy packed in there because this was a living thing many millions of years ago that had lots of energy itself. So the good thing about fossil fuels is they have so much energy to offer. The bad thing is that they emit greenhouse gases, which cause climate change, and we're only going to have a limited supply of these things for a certain period of time. After a while, they'll be gone. So that makes them a non-renewable resource. So that was coal. Before I get into renewable energy, I'm going to talk about one that's a little bit different that is technically non-renewable, which is equally as fascinating, which is nuclear power. And this is one that scares people from time to time, and we'll talk about why. But basically, in a nuclear power plant, you need to dig out of the earth something that is radioactive. Radioactive just means that it's giving off energy just by naturally existing, because things that are very unstable are trying to pop into things that are more stable. Google nuclear physics and get back to me. Anyways, energy that is stored in the uranium as nuclear energy is going to be transferred into heat energy. Heat is going to be released from the radioactive plutonium or uranium, and that heat gets transferred into water, which turns into steam because it's been made very hot. And so just like last time, steam is going to travel down a pipe, and the steam, the kinetic energy in the steam, that motion energy is going to turn into motion energy of the turbine, which is going to spin, and the turbine is going to go into a generator, which will convert the spinning into electrical energy, and that energy once again goes out to the public to plug in their iPhones. So that's the process. And the only thing that was different is the source of that energy, but the whole process of using that energy to create steam, to turn generator, all of that process is still the same at the end. So if we look at the energy breakdown, this is about a 35% efficient process, not too different from the last example. We get to keep 35% of the electrical energy. It's 35% efficient. The other 65% is heat that just leaves, and we never really get to grab that and keep it. It just escapes into the environment. So that's nuclear power. Now, some pros and cons here, and these are going to be somewhat obvious if you know anything about nuclear power. You get a lot of energy out of this because plutonium and uranium are very highly reactive fuel sources, and they're constantly throwing energy off of themselves. And it's only by putting them in a locked container that we get to use all that energy. So the fact that there's no burning happening means that there are no greenhouse gas emissions. So that's another pro. A couple cons though, like fossil fuels, there's only so much plutonium and uranium underground that we can dig up to use. So eventually, technically, it will run out. Toxic waste is another issue. Radioactive fuel that has been spent, we would say, is still radioactive, but we can't necessarily use it as fuel efficiently. So it just kind of gets put in barrels or buried underground or sometimes even dumped into the ocean. So that's a problem. And of course, what people are most terrified of is that someone might someday make a mistake in a nuclear power station, or perhaps terrorists might try and attack a nuclear power plant and take it over, because then a possible radiological disaster could occur, like in Chernobyl, Ukraine. So moving on to our next fuel source, here's our first renewable example. We're looking at a hydroelectric dam, sometimes called a hydroelectric power station. So the way this works is pretty interesting. When water is dammed up, it has a lot of stored up potential energy, which means it has the energy to potentially do work, but it hasn't started falling or moving or doing anything dramatic yet. It's stored up energy. If you build a dam and you contain all that water, but then you allow a small channel of the energy to flow through the dam, then that is going to be your source of capturing the energy. So the potential energy in the water turns into kinetic energy in the water where it starts moving, and that water then rushes by a turbine which spins it, and that turbine then cranks a generator which creates electricity. So again, the end product is pretty much the same as last time, but the beginning, the way we got that initial energy, is a little bit different. Now this is a very efficient process because water, as opposed to steam, contains a lot more motion energy to it because it's denser. So it has more oomph when it hits that turbine. So the energy we get to keep is about 80%, the waste energy is about 20%, and there's no real heat going on here. Nothing is very hot, nothing's burning, so the waste energy lost due to heat or other things is pretty minimal, so it's an 80% efficient process. A couple pros and cons here. There are no emissions because there's, again, no burning happening, but the cons are you need to have some kind of large water source like a river or a lake that you can dam up. And when you dam a lake, you're preventing fish and other animals from using that water source the way that it was intended to be by nature, let's say. So Fish that usually transport themselves down the river can no longer do so, and nutrients can't cycle, so things get disrupted. So that's a con that a lot of naturalists or environmentalists would take issue with. So now we're going to look at something a little bit different called wave power. Now in this case, what they've got is a little cone that sits right on the surface of the ocean. And you guys know that waves flap up and down, and what that does is it pushes the air up and down just above the surface of the water. So there's a little turbine that will spin as a result of the fan blades being pushed by that air that's moving up and down. So the air spins the fan blades, which spins the generator, which turns into electrical energy. Same thing we've got going in the last couple examples. You can even see the wire in this case that goes from the generator all the way down to wherever the electricity is going to be sent to. In this case, it's pretty inefficient getting our energy in this case because the air that's inside of that cone is not always going to be going directly up into the fan blade, and the water's not always going to be flapping up to push the air in that direction. So there's a lot of kinetic energy in there, but most of it's not being used. In fact, about 70% of the energy is lost due to just not being usefully used in the right direction. 30% we get to keep, however. So that's wave power. Now a couple pros and cons here. The pro is that we have a constant supply because we're not going to run out of waves anytime soon unless the moon explodes or something. And if that happens, we have bigger problems to worry about than the fate of our wave power stations. And also there are no emissions because since this is happening in water, there's no burning happening. A couple cons. It does require a water source. Obviously, you've got to have water to have waves. And it can disrupt marine ecosystems that live in the area that we install the station at. Another one that's kind of similar is tidal power, which is related, but it's different because if you notice, the fan blade that's being spun is now being spun by the left to right or forward and backward motion of the tides, as opposed to the up and down motion of air above the water's surface. So water is being used here to push this vertical fan blade. In fact, it kind of looks like a wind turbine that you'd see on land. It's just deep underwater. And the tide motion, the kinetic energy of the tides or the current, spins the fan blade, which turns into electricity via a turbine and generator combination. So we get to keep 40% of our energy, we lose about 60% of it, and here are our pros and cons. The pro is, of course, no emissions because no burning, and the con is you have to build these in very specific coastal locations, and that's it. You obviously can't do this on land, and you can't do it at a spot in the ocean where there isn't high tide or where you can't access the station that you've built easily. Next on our list is wind power, which is a pretty popular one. The kinetic energy of the wind that flows past these fan blades is going to turn into rotational energy in the turbine, which will create electrical energy. We get to keep about 40% of the energy from this because there's just so much wind blowing in all manner of directions. Not all of it's going to go exactly straight on into the turbine itself. So we lose about 60%. This is a therefore 40% efficient process. Couple pros and cons. There are no emissions because, again, there's no burning happening, and it is cheap to run because wind is free, in case you didn't know, and you can even put these offshore out in the ocean if there's a really, blustery location offshore. A couple problems, though. They are noisy, so if you ever actually go on YouTube and look up footage of one of these things turning, you can actually hear it really loudly. In fact, it kind of sounds like an airplane engine running. So you don't want to have your house right next to one of these or they'll be very unpleasant. You won't want to be outside like ever. Another problem is some people think that they aren't aesthetically pleasing and that they ruin the landscape. If you are, at a park or if you're on the ocean, people say they don't want to look out and see an expanse of wind turbines. They want to see nature, and that's it. So I think they look beautiful just the way they are, but some people think they look ugly. Ugh. Non-scientists, am I right? And also, probably the greatest drawback of all of wind power is that there's no power if there's no wind. So these are only producing energy sometimes, not all the time. And that means we could never possibly just rely on wind power. Now, another fuel source is called biofuel. And this is anything from wood to moss to mulch, organic matter that we get from the forest, let's say. This stuff can be put into a bin, which can then be lit on fire, and the ashes from that fire will be generally collected downward, but some of it will go up into the air as air pollution, and so that's kind of a concern. But as we've seen in the past with things that are burned, their burning is used to heat up water, which turns into steam, and the steam will flow through a turbine, which in turn goes to a generator to create electricity. So similar to what we've seen before. The pro here is that since you're using biofuels, literally things that are biological and grow back, trees will grow back if you cut them down, we do have a regenerative supply. So this is considered a renewable resource, as long as you consider the fact that you're not going to grow a tree back just like that. You've got to wait for that. The con is, of course, that there's air pollution, and to be totally honest, you don't really get that much energy out of biofuels compared to nuclear energy or even solar and wind. So it's the kind of thing that you might do in your house, but the factory size operation that we've talked about with other power sources is not going to be as commonly seen. We'll go next to an extremely popular option, which is solar power. What we're looking at here is a diagram of a solar power field, and you'd see these very often in large open savannas or deserts or fields where there's lots of flat area, because if you can get lots of solar panels all lined up in a very large scale operation, you can collect quite a bit of energy just from letting these panels sit there. Now it's pretty interesting how these work. Basically, to simplify it, sunlight comes down and strikes a very special kind of metal, and that metal sends electrons flying up itself because it was struck by light energy. So that's an extremely simplified version of how it works, but that's the basic idea. We get to keep about 30% of the energy that is converted from light energy into electrical energy, and the other 70% is either heat or motion energy, things that are just lost. The pros of solar power, as you can imagine, is that there are no emissions because there's no burning. And one really nice thing that a lot of people sometimes don't think about is that you can have large-scale solar operations, or you can just have a solar-powered charger on your backpack, or you can have a solar-powered charger for your phone that sits in the windowsill in your house. And so these can be any size. There have been solar-powered calculators in schools for decades. So it's a really cool technology because of the different scales that you could possibly have with it. But there are some cons. The con is that if you've ever tried to get solar panels installed on your house, you'd find that they are very expensive up front. It does pay for itself after many years, but it's not cheap initially. And again, like wind power, it's not going to always supply energy. It's only when the sun is beating directly down on the panels, at a 90-degree angle, that it will be giving out its maximum potential of energy. It's still going to get a little bit of energy out if the sun is off at an angle, but if it's at 90 degrees, that's its maximum output. So pros and cons, just like everything else. And the last example I'll give is geothermal power, which doesn't really have as many cons as some other types of energy sources that we've talked about, but it's still not perfect because it can only be put in certain locations. So if you have a geothermal vent below your factory, and that means specific locations only, if you have a geothermal vent that allows heat from the inside of the Earth's core to move up towards the surface, then you can capture that heat and you can use it to turn water into steam, which can turn a generator, as we've seen in the past. And it's pretty efficient, all things considered. You get to keep about 40% of the energy that comes out. And to replace the hot water or the hot chemicals that were flowing up, you have to then pump cold water down to replace it. So technically this is infinite, because if you think about the size of the Earth compared to the size of a factory, one factory is never going to be able to deplete all of the heat that's in the Earth, and the heat in the Earth is being constantly replenished due to nuclear reactions that are occurring down there. So this is considered a renewable resource, even though technically I suppose it's physically possible for us to take all the energy out of the Earth all at once. Realistically, that would never happen. So this is considered renewable. And so here are some pros and cons for geothermal. There is a constant supply, as I mentioned, and there are no emissions, but as I mentioned, of course, as well, it can only be built in specific locations. Now, you can also have geothermal power in your own home, and that might look a little different. That might look like tubes that just connect literally the dirt a few feet below your house with tubes to the inside of your home. And what that would do is it would make an equilibrium between the temperature of the soil below your home and the air inside of your home. And so if in the wintertime the ground is warmer than the environment, then the warmer ground will heat your home. And if in the summertime it's really hot outside and therefore it's colder in the ground, then connecting the ground to your house means that you're going to cool down your house. So the ground has a very stable temperature, and so that means in extremes it can kind of help to balance out the temperature of your home. And that's a little different than the diagram you're seeing here, but that's the basic idea. So those are all the different types of energy that we're going to be discussing for now in class. I hope you learned a lot, and if you want to review anything, feel free to just rewind the video. I'll see you guys in the next one. So long.